Ever look up at a massive airliner cutting through the sky and wonder how it's even possible? How does it navigate the entire globe with pinpoint accuracy, dodge storms, and even land itself when the pilots can't see a thing? Well, it's not magic. It's this complex, invisible world of electronics working silently behind the scenes. So today, let's pull back the curtain on this hidden network and explore the incredible world of avionics. Just look at this. A cockpit from the 60s was a literal sea of dials. Hundreds of individual analog gauges, each one doing one single job. It's overwhelming just to look at. Now compare that to a modern glass cockpit. It's clean, it's simple, just a few big digital screens. So what on earth happened? What caused this massive transformation? Well, it was the evolution of the aircraft's electronic brain. And that brain has a name, avionics. It's a mashup of aviation and electronics, and it covers pretty much everything. We're talking navigation, communication, the flight controls themselves, all of it. The best way to think about it is as the aircraft's central brain and nervous system. It's what's processing all the information and sending out commands to make the entire flight happen. To really understand how we got to these slick cockpits we see today, we need to look at how that brain evolved. And really, it's a story of moving from miles and miles of heavy single-purpose wires to these incredibly powerful integrated computers. You can really see the progression here. Back in the 60s, every single system was its own separate box, hardwired to do one thing. Then in the 70s and 80s, we started getting digital data buses, which was a huge step forward, allowing systems to talk to each other. But today we have something called Integrated Modular Avionics, or IMA. Think of it like this. You've swapped out a dozen different old gadgets for one powerful smartphone. You have these common computers that share processing power. And that doesn't just simplify things. It massively cuts down on weight, which makes planes more fuel efficient and way more reliable. Okay, so we've got this super powerful brain on board. How does the pilot actually interact with it? Well, it all starts before the plane even leaves the gate by programming the perfect journey from point A all the way to point D. The main tool for this job is the Flight Management System, the FMS. You can think of this as the pilot's mission planner. This is where they put in the entire flight plan, and the system is smart enough to pull in all the navigation data, calculate the plane's performance, and even figure out the most efficient way to manage fuel for the whole trip. It's the whole shebang. So how do they actually use it? Well, it breaks down into 3 key steps before they take off. First step, position initialization. They tell the plane exactly where it is on the globe. Step 2, route selection. They punch in the origin, the destination, and all the little checkpoints or waypoints along the way. And finally, step 3 is performance initialization. They enter the fuel load, the weight of the plane, and something called a cost index, which basically tells the FMS whether they should prioritize saving fuel or saving time on this particular flight. All right, the plan is locked in. How do the pilots actually fly the thing? Well, in modern jets, they use a system called fly-by-wire. This is a game changer. It means the pilot's joystick is no longer physically connected to the wings with cables and pulleys. Nope. Instead, their inputs become electrical signals that go to a computer. That computer then decides the best way to move the flaps and rudders. The computer is the middleman, and that's absolutely crucial because it makes the plane more efficient and even prevents pilots from accidentally making an unsafe move. All right, we're in the air, we're cruising. How does this electronic brain actually sense the world around it to follow that flight plan we just programmed? Let's talk about the eyes and ears of the aircraft at 30,000 feet. A modern plane knows its exact location with incredible precision because it's blending data from 3 different sources. You've got the inertial navigation system, which basically feels its own movement using internal gyroscopes. Then, of course, you've got GPS, pulling in super precise location data from satellites. And finally, there's radio navigation, which uses signals from stations on the ground. The FMS is constantly cross-checking all 3 of these to get the most accurate, reliable position possible. But it's not just about knowing where you are. It's about knowing what's in front of you. And for that, the plane has its own forward-looking eyes, the weather radar. It's constantly scanning the path ahead, specifically looking for precipitation, rain, hail, snow, because that's the #1 indicator of nasty storms and turbulence. And the pilots see this information as a really simple color-coded map. Green means light rain, no big deal. Yellow, that's moderate precipitation, so you might feel a few bumps. But red means heavy precipitation, almost certainly thunderstorms and severe turbulence. And the rule for pilots is simple. You do not fly into the red, period. So beyond just getting from A to B, avionics also includes a whole suite of what I like to call automated guardian angels. These are critical safety systems that are always watching over the flight, working silently in the background to prevent accidents. So, how do you keep planes from running into each other in a crowded sky? The first line of defense is TCAS, the Traffic Collision and Avoidance System. Every modern airliner has one, and these systems are constantly talking to each other, broadcasting their position and altitude. TCAS is like a digital lookout tracking all the nearby planes to prevent mid-air collisions, and it does this completely on its own without any help from air traffic control on the ground. Now, if TCAS thinks there's a potential conflict, it gives the pilots escalating alerts. The first is a traffic advisory, or a TA. It's basically the system saying, hey, look out, and it prompts the pilots to try and spot the other plane with their own eyes. But if that risk becomes critical, it issues a resolution advisory, or an RA. And that's an urgent audible command, something like climb, climb, that the pilots are required to follow immediately, no questions asked. The other guardian angel watching over the flight is the Ground Proximity Warning System, or GPWS. This system is designed to prevent an absolutely terrifying scenario called controlled flight into terrain. Using a radar that's always measuring the distance to the ground and a detailed terrain database, it will scream warnings at the pilots like, terrain, pull up, if the plane is ever in danger of flying into a mountain or the ground. All right, let's bring this plane in for a landing. We're moving to the final and most critical phase of the entire flight. And this is where precision avionics really takes center stage, especially when the pilots can't even see the runway. A safe landing in bad weather is made possible by the Instrument Landing System, or ILS. Now, this is a system on the ground that shoots out two highly focused radio beams from the runway. And together, these beams create a perfect, invisible highway in the sky for the plane to follow all the way down to the touchdown point. So the plane's avionics lock onto this pathway in two simple steps. First, it captures the localizer beam. That gives it the left-right guidance to line up perfectly with the center of the runway. Then it captures the glide slope beam, and that gives it the up-down guidance to ensure a perfect, constant descent angle all the way down. And this capability leads to one of the most mind-blowing feats in all of aviation. When the visibility is near zero, the autopilot can lock onto that ILS signal and perform what's called an auto land. The system will fly the plane down that invisible pathway, flare for landing, and put the wheels on the runway, all without the pilot ever touching the controls. It's just a stunning demonstration of all these avionics working together perfectly. So, when you see that level of automation, it naturally leads to the big question. What's next? Where is this ever smarter invisible brain taking the world of aviation? Right now, you could say the ultimate expression of avionics is the unmanned aerial vehicle, or UAV. Drones. Aircraft like the Global Hawk and Predator can fly entire, complex missions completely on their own or by remote control. They are the logical conclusion of this whole trend, a point where the invisible brain isn't just assisting the pilot, it is the pilot. And that really brings us to the final fascinating question to chew on. As these systems get smarter and more autonomous, handling everything from takeoff to a perfect auto land, will we always need human pilots in the cockpit? It's definitely something to think about.